Now that we've gotten a handle on double replacement reactions, it's time to turn our attention back to redox reactions. Now, if you remember, there are actually 4 different types of redox reactions, so it's going to be a little hard to do all of them at the same time. Instead, I'd like to focus on just 2 of them. For the first segment here, I'd like to focus on the synthesis and decomposition reactions. How do we predict the products of both of those styles of reactions? Now, the reason that I'm focusing on both of these at the same time is because they're essentially opposites of each other. From your notes, you probably have written down all of the different schemes here, how to tell the difference between synthesis, decomposition, combustion, and single replacement. I want you to take a notice that synthesis and decomposition are pretty much exact opposites of each other, where synthesis is essentially element plus element to make a compound, and decomposition is a compound which splits up into its elements. So let's start by taking a look at how do we predict the products from a synthesis reaction. More ordinarily, you're going to be provided with the elements themselves. Now notice both of these elements are written out by themselves. They're not paired with any other element symbol. So we know that these are pure elements. Don't let the little 2 behind the Cl confuse you. There's no other element symbols with it. It's still an element, even though it's diatomic. First step, we're going to take both of those element symbols, and on the product side, we're going to write them next to each other. Don't bring along any subscripts. The subscripts need to be left behind. We're going to create new ones on the product side. Anytime that you're writing the chemical formula for a new compound, you always start from fresh. So here's the Na and the Cl. Next up, find the charges of these ions on the periodic table and write them down. So for my Na, it's 1 plus. For my Cl, it's 1 minus. Next, crisscross them. So we're going to bring the charges down to the opposite corners. And if I did that for this one, I would have Na1, Cl1. Now don't forget that we never write the 1 as a subscript. It's assumed that if you have the element symbol there in the first place, you already have at least one of them. Time to balance the equation. All right, so when we go to balance, make sure that you have the same number of each type of atom on both sides. First thing that I notice is that my chlorines are out of whack. So I'm going to fix that by adding in a coefficient 2. Now that does increase the number of sodiums, so I'll have to fix that as well. I'll add in another coefficient 2, and my equation is balanced. Final step, add some state symbols. Now, we already had the state symbols for the elements, but I do need to predict the state symbol for the compound. Just as a reminder, you can predict the state symbols of compounds using the solubility rules found on the back of your periodic table. Luckily, sodium is a group 1 element, chlorine is a group 17 element. Together, they make an aqueous compound. Now, just as a reminder, Brinkelhoff does not apply to any compounds. So even though chlorine was inside the compound NaCl, because it's not by itself, Brinkelhoff does not apply. Now let's take a look at synthesis's opposite, decomposition. In this reaction, we'll take a compound and we'll split it up into its elements. Take, for example, NaCl. The very first thing that you're going to want to do, on the product side, write each element separated by a plus sign. So here we go, Na plus Cl. Next, check for Brinkelhoff. And again, this only applies to bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Now that's right, we do have an element here that applies to Brinkelhoff. But again, Brinkelhoff only applies to single elements, not to elements that are inside of compounds. So let's put a little 2 behind the chlorine. Next up, we're going to need to balance the equation. And finally, include the state symbols. Now, you may have forgotten where these state symbols actually come from. So how do you find state symbols for individual elements because they're not on the solubility rules? Don't forget that you can use a specially coded periodic table that will help you figure out the state symbols of pure elements. Almost everything on the periodic table is a solid, with the exception of two elements that are liquid: bromine, a nonmetal, mercury, a metal. And then to the upper right-hand corner is where you're going to find most of your gases, all of which are nonmetals.